Hello and welcome to follow my videos. My name is Matti Ylitalo and today our topic is time response of thermocouple. Just a second, I'll put the presentation mode on. Thermocouple is a very simple measurement device. It's based on so-called Seebeck effect. We have two different types of wires which are connected, and this connection point is the measurement location. Then we have this cold junction and some kind of device having this display to read those temperatures. And depending on the wires, we are talking about different types of thermocouples, so-called type K, type J, type T and type E. And those thermocouples are widely used in industry, and that's because the temperature range is very large. They can be used in very low temperatures and up to almost 2000 degrees C. In these pictures we see commercial thermocouples. On the left we have a wire, and at the end of this wire is this kind of end part. Inside which is this so-called hot junction, which is the measurement location. And on the picture on the right we have another thermocouple model. It's having this kind of protective housing around this measurement junction. One important question when we are measuring temperatures is how fast is our measurement device? If we have a change in temperature, the probe does not instantly equal that temperature, and that's because the probe has a thermal mass and the heat transfer rate is finite. Now our task is to define what is this time constant. If we have a thermocouple in environment which temperature is T infinite, we can write this kind of general equation. And here this tau is this time constant. And if we now have a step change in environment temperature from T0 to T1, we can write for thermocouple measurement junction temperature this equation. And here we have now this exponent term in which is this tau. And as a rule of thumb, we can say that at time, which is the same as this time constant, this change in reading is around 63% of the total change in environment temperature. And after T 3 times this time constant, the change is 95% of the total change. And after 5 times this tau, this change in reading is around 99.3% of that temperature change in environment. Here we have a function for this time constant. It is a mass of this thermocouple tip, inside which is this measurement junction, times this specific heat of this material divided by convective heat transfer coefficient times this surface area of that measurement tip. So we can say that the smaller the mass of this thermocouple tip is, the faster is this thermocouple, and the higher this convective heat transfer coefficient, the faster is our thermocouple. Here are some guidelines how you can measure this time constant of your thermocouple. For example, you can carry out this kind of step test and find out what is your time constant. Here we have an example in which our task is to calculate this time constant using Python code. And the initial data is that we know the material density, material thermal conductivity and thermal capacity. And we have a given value for this heat transfer coefficient. And the first question is that what is the junction diameter if we want the time constant to be 1 second? And the second question is that we need to calculate the temperature reading in case when we put this probe to 200 degrees C. I asked this code from ChatGPT and I calculated this case, and here we have the results. If we want this time constant to be 1 second, the required junction diameter is less than 1 millimeter. And I calculated also this Wyatt number, and it's very small, so this kind of assumption using this so-called lumped model is valid. And it seems that if we put this thermocouple to 200 degrees C, it reaches this 63% of this temperature change in less than 1 second, and it takes around 7 seconds to reach 99.9% of this temperature change. We need to be aware that when we measure with this kind of a thermocouple, it takes quite a long time to reach this final temperature. In this case, after 2 seconds, the reading is 175, and it takes around 5-6 seconds to go up to 200 degrees C. So the big question is that if our temperature is not this 200, if it is varying, so the question is that can this thermocouple follow those temperature changes? One typical problem when we are measuring with thermocouples in hot gas environment is the error coming from radiation. If the surrounding walls are hotter than the gas, then the probe reads too high values. And if the walls are cold, then it means that the probe reads too cold. Here are some guidelines how we can reduce radiation error. For example, we can use polished tips, and we can try to increase heat transfer coefficient and use smaller junctions, and if no other methods, we can try to calculate what is the effect of radiation. Here we have some guidelines how we can make our thermocouple fast. Basically, a smaller mass, smaller thermal capacity, higher heat transfer coefficient and higher surface area will give us a smaller time constant. You need to think what are your needs. If you are measuring a temperature which is constant, it's totally different compared to case in which your measured temperature is changing. if it is changing, you need to think, is your measuring instrument so fast that it can follow those changes? Okay, that was all this time. Thank you for watching and see you. Bye bye.